Hello everyone and welcome back to the sixth day of Astronomy Week organized by Astro Club of Fergusson College. Until now we have seen talks starting from Big Bang up to optical and radio astronomy. Is astronomy only limited up to electromagnetic spectra? Answer is definitely no. I am Prabhanjan Kulkarni and let's try to understand recently discovered new branch of astronomy, that is gravitational waves. In this talk, I will be speaking about gravitational waves. How were we able to detect gravitational waves with LIGO? Also, we will discuss about the future projects related to this branch of astronomy. Albert Einstein, in his paper of General Theory of Relativity, predicted the existence of gravitational waves. His equations showed that massive accelerating objects would disrupt the space-time and create the ripples. These ripples are known as gravitational waves. In the left side image, you can see a 3D model of space-time. As the particle moves, it creates the curvature. Now, instead of a particle, consider a binary neutron star system. As the neutron stars orbit each other, they will create waves in fabric of space-time. These waves will move away from the source. In 1974, two astrophysicists, Russell Hulse and Joseph Taylor, discovered a binary pair of neutron stars 21,000 light years from Earth. They noted that the time it takes for the two stars to orbit each other was decreasing exactly same as general theory of relativity predicted if the two stars were radiating gravitational waves. After 40 years of continuous research, scientists were finally able to detect the gravitational waves and new era of astronomy began with this beautiful paper. Similar to every other wave, gravitational waves have properties like energy, angular momentum, redshift and polarization. When two black holes collide, some of the mass gets converted into energy in the form of gravitational wave. A binary system loses angular momentum and spiral towards each other. Its angular momentum is radiated as gravitational wave. If two supermassive black holes collide, their linear momentum can produce a kick. Due to this kick, new formed black hole may get ejected from its host galaxy. This picture, which is focusing a galaxy, is thought to contain such a recoiling supermassive black hole. If a plus polarized gravitational wave passes through some particles, then particles will behave like this. If a cross polarized gravitational wave passes through some particles, then particles will behave like this. Albert Michelson invented optical interferometry. Michelson's interferometer is the common configuration used for optical interferometry. The setup for Michelson's interferometer is quite simple. We have a source, two mirrors, of which one is fixed, one is movable, one beam splitter, one compensator, and one detector. Now for some time we will forget about compensator. So the process is quite simple. Source will emit some light beam which will incident on beam splitter. The beam splitter will split the light beam in two parts. One part will go towards the movable mirror and another part will go towards the fixed mirror. Now the light beam which went towards the movable mirror will cross the beam splitter thrice, whereas the light beam which went towards the fixed mirror will cross the beam splitter only once. So there is some difference between the optical paths of those beams. We don't want this optical path difference. That's why we will introduce something called as compensator in the system. Now this compensator is of same thickness as of beam splitter and is made of same material. So now both the beam will pass through so-called beam splitter thrice, and that's why we will be able to see the interference pattern at detector. Also, one thing we should note that if the distance between movable mirror and fixed mirror from beam splitter is different, then only we can see the interference pattern. The Michelson's interferometer's idea was taken for the construction of LIGO. Laser Interferometry Gravitational Wave Observatory is partially based on working of Michelson's interferometer. Let's see some of the similarities between both of them. They both are L-shaped. Not all interferometers have this shape. Then they have mirrors at the end of the arms which reflect light in order to combine light beams and create an interference pattern. They measure patterns and intensity of a resulting light beam after two beams have been superimposed or forced to interfere. But this is the end of the similarities. Size of LIGO is far beyond than that of Michelson's interferometer, and same case goes with the complexity of LIGO too. LIGO's interferometer are largest ever built. Also, they have the maximum sensitivity in all Earth-based scientific instruments. These two are the sites of present LIGO observatories. First is Livingston Observatory from USA and second is Hanford Observatory. Gravitational waves are very hard to detect. Smallest possible noise like a sound of walking man or movement of tectonic plates can disturb the readings for gravitational waves. So the question is, how did we achieve sensitivity of LIGO? Let's see all of the below points one by one. Arms of LIGO are 4 kilometers wide. We want to make such arms along with controlled ultra high vacuum in them. So it is quite difficult to make this thing and to maintain such things. So to make these arms, the tubes were heated from 150 degrees Celsius to 170 degrees Celsius continuously for 30 days. This was done to remove residual gas molecules from them. Now we want to create vacuum inside these tubes. That's why turbopumps were used. These turbopumps sucked out the air contained in them in the tubes. To create vacuum is another part and to maintain such vacuum is another. So ion pumps were installed in these tubes. These ion pumps continuously extract individual remaining gas molecules from the tubes and throw out in the. So now we have seen how the arms of interferometer made and how the controlled ultra high vacuum was created in the arms of interferometer. Let's see some information about the mirrors of the mirrors of LIGO are called as test masses. These test mass weighs 40 kg each. These test masses are made up of very pure fused silica. The polishing of mirror is so precise that difference between their theoretical design and actual design was measured in atoms. Out of 3.3 million photons, these test masses only absorb 1 photon. Due to this, the heating and the distortion because of heating is reduced in these mirrors. Also, due to the less absorption, or we can say almost zero absorption, the power of laser is also preserved. These test masses happens to refocus the laser if a laser is not focused. Now we have talked about the mirrors, let's talk about the mirror stabilization techniques. Why this mirror stabilization is so important? So say the mirror is not stable and the laser beam incidents on the mirror, when it will merge with the another beam, it won't be in proper phase with the other beam, and that's why it won't be able to create the interference pattern at the detector. So this part is quite important in to achieve sensitivity of LIGO. So in mirror stabilization, we are going to see about the seismic isolation system and suspension system. LIGO's mirror must be well shielded from any vibrations, and hence two damping systems have been installed in these detectors. First one is active damping and another is passive damping. In active damping, internal seismic isolation or ISI comes into the picture. This ISI contains devices which counteract any ground movement. Also in this system, there are various sensors which detect various frequencies caused by the nature. This data is then relayed to the computer, which after analyzing the data send the command for counteraction to respective devices. In passive damping, a four-staged pendulum, which is known as quadruple pendulum or quad, is used. The quadruple system is actually the system of four pendulums, and that's why the name quadruple. In this quad, two chains of suspended masses hung back to back in each suspension system. In main chain, upper two masses are made up of metal, whereas lower masses are made up of pure fused silica. Lowermost cylinder in the main chain is the test mass suspended by glass thread of thickness 0.4 mm. Reason to use glass threads is that they do not contract or expand due to the temperature variations. It is important that distance between test masses at the end of each arm should not move more than a fraction of a picometer. This is where reaction chains come into the picture. The upper two masses of the reaction chain are controlled by simple motors, which are made up of permanent magnets and electrical coils. This system carefully pushes the test mass to keep it steady. Now we have studied about the arms of the interferometer and mirrors and the mirror stabilization or suspension systems. So now let's move on to the next topic, which is the light source of LIGO or the laser of LIGO. Laser of LIGO is near infrared laser. Firstly, it is made by using laser diode, which uses electricity and generates a beam with power 4 watt and having wavelength 808 nanometer. In any other shelf laser, laser diode is used, but the LIGO's laser is 800 times stronger than everyday laser. This generated beam is then passed from fingernail size crystal, which converts the laser beam into 2 watt beam with wavelength as 1064 nanometer. This fingernail size crystal is called as non-planar ring oscillator. This beam is called as SID. This SID beam is passed from master oscillator power amplifier or MOPA. It contains 4 rods, which are the laser amplifiers. They are about the size of pencil. For amplification, these rods are energized by shining different laser of 808 nanometer. When the seed beam travels through these rods, they generate new photons of wavelength 1064 nanometer with same properties. After the first rod, the process repeats for all remaining 3 rods. At the end, we get laser beam of 35 watt power and 1064 nanometer wavelength. The last stage of amplification is completed using a device called high power oscillator or the HPO. This HPO consists of 4 rods about the same size as the MOPA but made of different materials. As the beam travels through the rods, it gets additional power boosts from laser light funneled through bundles of fiber optics. Each fiber carries 45 watts and there are 7 fibers, so each bundle delivers 315 watt into each HPO rod. At the end, when the beam exits the HPO, it has finally achieved its desired power of 200 watt and its desired wavelength 1064 nanometer. This is how everyday lasers look like, and this is how the LIGO's laser looks like. You can compare the sizes and complexity between both of them. Now we have completed everything which was on the list. So you might be thinking that we might have achieved the sensitivity of LIGO. Well, sorry to disappoint you, but not yet. So what additional techniques are used to achieve the sensitivity of LIGO? Let's see those techniques. LIGO's arms are 4 kilometers in length. It seems pretty huge, but they are too short to detect any gravitational wave. Also, we can't build such precise instruments which are longer than 4 kilometers due to practical limitations. So scientists found a solution that included something which is called as Fabry-Perot cavity in the arms of LIGO. Let's see how this Fabry-Perot cavity works. Consider two bireflective mirrors. When a light beam incidents on a first mirror, it will refract and then incident on the second. Here, everything changes. At the second mirror, the beam of light gets splitted in two parts. One get reflected and another get refracted. The reflected beam again reflects from first mirror and incident on second mirror. Again, the beam gets splitted in two and the process continues. The refracted beam incidents on a lens and gets focused on detector which is kept right next to the lens. So, in LIGO, when beam of laser enters the cavity, the beam bounces between its two mirrors for about 300 times. This effectively increases the optical length of the arm to about 1200 kilometers. So, problem solved. So, increasing the length increases the sensitivity, but increasing the power of laser, resolution of instrument is increased. But we can't make more powerful laser than we already have due to practical limitations. We can't build a laser that powerful, but we can recycle the power of laser which is already there, right? So scientists introduced power recycling mirrors into the system. So in interferometer, the light beam passes from the transparent side of power recycling mirrors to the beam splitter and then inside the arms. The beam splitter is designed so that almost all of the laser light entering the arms comes back to the reflective side of the power recycling mirror rather than going towards the photodetector. As laser is constantly entering the interferometer, the power recycling mirror continuously reflects the laser light back into the interferometer. That's why it is recycling. This process boosts the power of laser beam inside the Fabry-Perot cavity. So now that we have seen how LIGO works, let's see an animation related to the merger of two black holes. This video was created by LIGO LSC to demonstrate the merger of two black holes and the production of gravitational waves because of their merger. At the bottom, you can see there is one graph which is amplitude versus time, and above that there is, you can see a zoomed version of two black holes which are orbiting around each other. As they orbit each other, they are generating gravitational waves, and as they come closer and closer, the frequency of generation of gravitational waves is increased. When they are too close, they will combine in each other, and that's where we will observe the peak in our data. After their merger, the source will stop production of gravitational waves, and hence we won't be able to see gravitational waves later, and that's why the graph is zero line. This video shows that how gravitational waves can sound, and I know that we cannot hear anything from space, but we can generate a signal using electrical devices which corresponds to the data that we have received. So this data is from the gravitational wave merger of two neutron stars, and the name of the gravitational wave is GW170817. Also, there is, in the upper part you can see that there is data of Fermi which detects the gamma rays which detected the gamma rays produced because of this merger. So that this video also shows that the speed of gravitational waves and electromagnetic wave is almost same, and this was the huge discovery for the field of gravitational wave astronomy. So this is the photo of masses in stellar graveyard. You can see here, this is the y-axis, and there are some numbers written 1, 2, 5, 10, 20, and so on. These numbers are in the unit of solar masses. So basically it is multiplied by the solar mass. It is times of the solar mass, you can say. You can see that here are some blue dots, or these are the LIGO Virgo black holes, or the black holes which were detected by LIGO Virgo. And these are some electromagnetic black holes which means that they were detected using the electromagnetic spectra. And here are some neutron stars, and this was the only detection of neutron star which we have observed till now. This photo is from 2018, so it is a bit older. You can see that these two black holes have merged to form this new black hole. So these are the actual parent and daughter black holes, you can see. And here this is parent neutron stars which forms something else which we don't know yet. You can also see that between two solar masses and five solar masses, there is no merger which we have detected. So this part is called as the mass gap. Recently on an app called Chirp, LIGO sent an alert about possible detection between this mass gap. So we should expect some research paper in near future related to this mystery. And also there are various, so recently another new uh, merger was announced, and which said that two asymmetric black holes were merged. So till now we have seen that mostly all the black holes are of same masses, but the recent discovery states that it is the merger of two black holes, which one is of 5 solar masses and another is of around 30 solar masses. This is the first time we have detected such kind of black hole merger. So now let's talk about some future projects. And the first project is LIGO India. So this is the proposed site which will be in Maharashtra in at Aundar Nagnath, and this is how the LIGO India will look like. So these are the arms of 4 kilometer length, and here is the main center, then and everything else. So for this, various institutions have came together, and the IUCAA from Pune is one of the leading institute. So after announcement of LIGO India project, where many people asked about why do we need a third LIGO observatory when we already have two LIGO and one Virgo observatory. So the reason is about the localization accuracy. So if if you consider two LIGO and one Virgo observatory, then you can see that there are some uh, points where we cannot localize where we cannot detect the gravitational wave. So these points are given by the red crosses in this image, as you can see that. So there are many points where we cannot detect the gravitational waves. But if you introduce this the third LIGO observatory, which is situated in India, you can see in this area there is no such error margin, and that's why the localization accuracy has increased drastically. Also, if we introduce a new LIGO observatory, then the baseline will increase. Uh, Currently, the two LIGO observatories are situated around 3000 kilometers apart, and if we introduced another LIGO observatory on another face of Earth, then the baseline will increase, and and also the localization accuracy will increase. So next future project is LISA, or Laser Interferometer Space Antenna. This project is led by European Space Agency in collaboration with NASA. The idea is to send three satellites in the space and to form a triangle like this and detect the gravitational waves. So this there is a reason behind this idea, because we cannot make a detector which has arm of around of more than 4 kilometers and with optical enhancements, let's say 1200 kilometers. But in space we can make these arms for millions of kilometers long. And this is the only reason why this project was launched, to detect the gravitational waves which are undetectable from Earth. The idea is to send these three satellites in the space, which will form the such kind of triangle. And these triangles, the center of this triangle will be behind Earth at 20 degree from Sun. If this angle is 20 degree, then this will be the center point of this triangle, and the distance between the Sun and the center of this triangle will be 1 astronomical unit, that is same as the Earth. Also, this LISA or interferometer will be inclined to the ecliptic by 60 degree. Uh, the distance between Earth and this center will be around 5 to 10 raised to 6 kilometers, and the distance between two satellites will be around 2.5 million kilometers. Uh, the this project will open up a new face, or this project will show us a new face of gravitational waves and many more secrets about our universe. Uh, the Recently the Pathfinder project for Lisa was launched, and till now it is quite successful, and it is giving data with quite precision. So it is expected that this Lisa project will be launched soon and will be functional in coming years. Thank you for your kind attention and watching this video. I hope this video was informative. If you have any questions or queries, you can write them down in the comment box. I will surely try to answer them. Do not forget to like, share and subscribe our YouTube channel. Thank you.